Hello, everyone. In this lesson, I'm going to tell you a little bit about how a magnetic force works on a moving charge. So just a quick recap of what we talked about the last few lessons. First, in the last lesson, I talked about how Ørsted made this discovery that a moving charge, so like a current in a wire, created a magnetic vector field. Right? So if you remember, if this was our current, right, if this was our wire, the magnetic field was given by the right-hand rule, where you take your right thumb in the direction of the current and you curl your fingers, and that gives you the magnetic field. All right. So that's one type of geometry, the wire, right-hand rule. The other types of geometries we talked about were loop and the solenoid, the coil. Solenoids are particularly useful because inside of that solenoid, inside of that coil, they produce a very high or very strong magnetic field. And theoretically, outside they have zero, but that's not quite right. But anyway, the point is that inside of the solenoid, they have a very strong magnetic field. Okay, so now that we've got this now that we know how to create a magnetic field, then we're going to go to the next thing, which is the force. That's something that a charged particle might experience while in that magnetic field. So just like what we talked about a couple days ago, or a couple lessons ago, when a charged particle enters an electric field, it experiences a force. And the same thing holds true when a charged particle enters a magnetic field. Okay. Some of the important variables in this case are the magnetic field, which we give the variable b. Don't ask why. The velocity of the particle and the charge on the particle. So different variables matter for magnetic force than do electric force, but one that is the same is the charge on the particle. So this is the formula for the magnetic force on a moving particle, right? So you can see there that QVB sine theta is our equation for the magnetic force, and that sine theta, that's the angle between how the magnetic field is pointing and how the charged particle is pointing. Okay, so for those of you who've done your vectors and calculus course, or doing it now, anytime you see something that's got a sine theta in it, and we're talking about vectors more broadly, you might think, okay, wait a minute, I know a law, or I know a formula that involves vectors and sine theta. Okay, we'll get back to that one in just a second. Okay, what's key here, and what will hopefully jog your memory about that, about the vector stuff, is that the force is perpendicular to the velocity and the magnetic field. So in other words, if I have a velocity, let's just say like this, if I have a velocity like this, and I have a magnetic field, velocity like this, and a magnetic field like this, then the force would be that way, would be into the screen, for example, okay? Because we've got to be perpendicular. So this comes out as a cross product, okay? If you haven't guessed it already, the idea here is we're looking for a cross product between the vector velocity and the vector magnetic field. Now, what might not be obvious, and especially if you're going to think about this, is if this is my velocity vector like so, and this is my magnetic field down, then the force will be in the direction of the palm of my hand, so into the camera in this case. And so in that case, my particle will experience a force that will make it curve like this, right? It will curve. It will actually turn. It will travel in a circle. Because my thumb, it will always be down, right? The magnetic field will always point down, but the velocity will slowly change because there's an acceleration, actually, right? There's a force into the camera, so an acceleration, in other words, that will turn the particle like this. So thinking back to near the beginning of this course, as soon as we have something accelerating inward into a circle, then we know how that goes. We know how that looks in terms of Newton's second law. Right. So, okay, so let's look at a possible application here. This one is a little esoteric. I don't know if you've ever heard of this before. I hadn't before I learned of it a few years ago. But there is something called a magnetohydrodynamic force, which you can actually use to move a watercraft without a motor. Right? Like if you've ever gone boating, then you know that you can either use an outboard, you can use some kind of outboard motor or something, or if you have a canoe, you can use a paddle. There's another way to move a boat, and that is without a motor whatsoever. And it's actually using this concept. So the basic idea, okay, well, I'll get back to that one later. The basic idea for this magnetohydrodynamic force is you have a boat, which this works best in seawater because seawater actually has free charges in it to an extent that freshwater does not or will not. So in this case, I hope you can see from the graphic here that we have two electrodes, and those sit in sort of the bottom of the boat. Seawater enters through an intake, and then you basically have this electric field you have an electric current between the electrodes, okay, and then so that's basically your charged, right? Your velocity vector is going that way, and then your B field is up, and you have a force backward. So kind of interesting there, kind of interesting design. Magnetic forces are also used for plasma containment. So if you ever hear about fusion reactors that use tokamak geometry, it's basically like a gigantic donut or toroid, torus. So in that case, the plasma is kept inside of there using very strong magnetic field containment. Okay, let's look at a problem here. Okay, so the first thing is we have an electron accelerates from rest in a horizontally directed electric field through a potential difference of 46 volts. Then the electron leaves that electric field and enters a magnetic field of magnitude 0.20 Tesla. That's what that capital T stands for, Tesla. Tesla is the unit of magnetic field strength directed into the page. Okay. So let's have a think about how. So I'm going to just draw a little doodle here showing what's going on, and then we're going to try and have a think about these three questions. So first, calculate the initial speed of the electron as it enters the magnetic field, calculate the magnetic force on the electron, and calculate the radius of the electron's circular path. And you're going to see that this problem actually not only brings in the new material, but also goes back to some of the stuff that we started with even at the beginning of the course. Okay, so I'm just going to doodle something up here, and then we'll look at this problem. Okay, so here I've done a little doodle just to show what's going on in this situation. So the first thing is that we have a parallel plate geometry here with an electric field, and the electric field is pointing from right to left, okay? And it doesn't say that in the question, but it says the electron is accelerated, and it's going to leave the parallel plate geometry. So here's a little exit hole. So I'm going to remember that electric field lines are always drawn with respect to what a positive charge would feel. So in this case, if we had a positive charge, it would go that way. But in this case, we have a negative charge, right? An electron is negatively charged, so it's going to go to the right. And then the electron is going to pop out of this plate here, and then it's going to be in this region of space where there's no electric field, but there is a magnetic field. And so the magnetic field is directed into the page. And so things that are directed into the page are represented with these X's here, right? X's usually with a circle around them. So that just shows that our magnetic field lines are going into the page. Now in this case, bear in mind that my velocity is going to be in this direction. So I'm just going to draw that. So my velocity will be this way. Okay, like so. So there's my velocity. That's the velocity vector of the electron as it's leaving here. Well, I'm just going to draw it here just for the sake of simplicity. And then my magnetic field is this way. Okay, so it's going to be that way. So again, for those of you who have done your vectors course, I want you to think about this. Our force is going to be coming from the vector cross product of V cross B, right? B is this, B is all this business here. This is my B. Okay, so think about this for a second. If you use your right hand and you do this cross product, which way should the force be? If it's V cross B, which way should the force be? Okay, I want you to think about that in your mind before I show the solution. You got it? Write it down. Write it down on a piece of paper next to you, just so that you don't forget. Okay. Okay. Then we're going to go back. All right. So here we are. All right. So here we are with this problem again. So the first thing we're going to do is we're going to calculate the initial speed of the electron as it enters the magnetic field, and then calculate the magnetic force on the electron, and then finally calculate the radius of the electron's circular path. So let's go through that first problem and how to solve it. So what we're going to do here is we're going to use energy conservation. So if you remember from energy conservation, the energy that we have at the beginning is equal to the energy that we have at the end. That's the law of conservation of energy. But in this case, there is actually work being done by the electric field. So that work being done by the electric field is Q delta V. That's the work done on the electron as it's in the electric field. And then as it leaves the electric field, then it only has kinetic energy. So that's our 1/2 mv squared. If you rearrange that, then you get the equation for the speed of the electron as it exits the electric field. And if you plug in the numbers, you get 4.02 times 10 to the 6 meters per second. Okay, so that's the first one. Again, because we were looking for the speed of the electron as it leaves, then speed basically is a scalar, and so we all usually want to use some kind of a scalar solution, something that gives us a scalar. And energy is usually the correct way to do it. So now that we have our electron, it's been accelerated up to 4.02 times 10 to the 6 meters per second, and now it's going to interact with the magnetic field. And so now we want to figure out what kind of force, or how strong of a force will the electron feel. So in order to do that, we have to use this equation for the magnetic force on a moving charge. And also remember to use your right-hand rule for the direction. So keep in mind that for these values here, the Q is the charge on an electron, which is negative, by the way. The speed we just figured out. B is that 0.20 Tesla, and sine theta is going to be the theta is going to be 90 degrees because the B field and the velocity of the electron we're taking to be perpendicular to one another. Okay, so the right-hand rule is the direction. It gives us the direction though. Okay, so if you put all the numbers in, then you get a force of 1.3 times 10 to the negative 13 newtons down. Now, some of you might have thought it should be up if you were using your right-hand rule properly. Why would it be down? Why would it be down? Well, remember that the electron is negative, so that means that the way the right-hand rule is proposed is it assumes that the charge is positive, right? If it were a proton, for example, then the force would in fact be up, but the electron has a negative charge, so basically you always have to flip your right-hand rule for an electron, right? You have to reverse the direction from what it would normally say. Okay, so now that we have the force, right, that magnetic force, now our electron is going to be undergoing some kind of circular, sorry, I guess it was like this, right? So this is the electron's motion. The magnetic field is into my face, and it'll be doing some kind of downward circle, something like this, and we want to know how that's going to go. So we're going to use Newton's second law, but for circular motion. And so if we neglect gravity as being very small in this case, which is fair, then the only force that gives us our circular motion is this magnetic force. And so again, if we assume that the sine theta is always equal to 1, meaning that the velocity and the magnetic field are always perpendicular, which is a good assumption in this case, then we get this nice simple equation. We can look through and we see that the speed shows up on both sides of the equation, so one of those will drop out, and we'll get the radius is given by mv over qb, so mass times speed divided by charge times the B field. And in this case, we'll get 1.1 times 10 to the negative 4 meters for the radius. So that's about a tenth. No, I apologize. Yeah, that's right. It's about a tenth of a millimeter, excuse me. So quite a small radius. Quite a small radius indeed. I mean, it's an electron, right? You wouldn't be able to see it with your eye anyway, but you know, whatever. Okay. So one device that gets used quite a lot in science, right? In various kinds of science, physics, biology, chemistry, you name it, is something called a mass spectrometer, which is basically a way of separating particles depending on their mass or their charge, or both. In order to use a mass spectrometer, you need to have the particle needs to be charged, because inevitably there's some kind of interaction with an electric field, or in this case, you could interact with the magnetic field. So in the case of a mass spectrometer, if you had, you could have two particles that had the same mass but had different charges, or you could have particles with different masses and the same charge. Regardless, the idea is that, just like we went through with this equation, is you would want to have those particles entering the field with where the magnetic field is, enter the magnetic field, and then they would do basically different trajectories depending on what their mass to charge ratio was. And so then by tuning the magnetic field, then you could basically collect the particles that you were interested in. So that's kind of what, so think of a mass spectrometer as basically a way of sorting, in a sense, different charged particles according to their mass or charge, or both. So I talked the other day about how the Earth's magnetic field basically protects us from cosmic radiation or charged particles, highly charged particles. So the idea is that there's some really neat graphics that you can see on this. Unfortunately, I forgot to include one. But the idea is that as those highly charged particles move close to the Earth, they will basically follow the magnetic field lines and will collide with the Earth's with the upper atmosphere, producing those beautiful aurora or northern lights, or southern lights, I suppose, if you're in the southern hemisphere. I already mentioned the magnetic containment for those tokamaks, those fusion reactors. Okay, so moving on to the second sample problem. We're asked to calculate the mass of chlorine-35 ions. So chlorine-35 means that it has a mass of 35 atomic mass units, and it has a charge of 1.60 times 10 to the negative 13 coulombs. So in other words, it has a charge of +1. Right? It has one missing electron, essentially. Accelerated into a mass spectrometer through a potential difference of 250 volts into a uniform 1 Tesla magnetic field. The radius of the curved path is 1.35 centimeters. So this is basically this idea of the mass spectrometer that I was talking about. So we're going to have our chlorine-35 ions. They're going to interact with our magnetic field, and they're going to go down or up, I guess, depending on how the magnetic field is pointing. It doesn't really matter in this case. And they're going to basically spin in some kind of circular path. Okay, so wait, what are we trying to do here? Oh yes, calculate the mass. I got it. Calculate the mass. So We don't need to necessarily go through this entire thing all over again, but this problem is going to resemble in some respects the one that we did before. Again, if we break this down into parts, you can see that the first thing we need to do is we need to know how fast these chlorine 35 ions are moving once they leave the electric field, right? So in other words, the first thing we need to know is how fast are they coming out of the electric field accelerator. Okay, so how's that going to go? Well, we're going to need the potential difference for that, and we're going to need the charge. So we've got those two things. Then, once it's out of that, it's going to be in the magnetic field, and we need to use this idea from Newton's second law, Newton's second law, but in the circular form, to figure out the radius, and that was the equation that we were working with a moment ago. Okay, so how's this going to go? First up, we're going to consider, once again, our energy conservation. And just like the last time, we're going to have our law of conservation of energy, where on the left-hand side, our electric field is going to do work. Oh, sorry, I don't know why I did it that way. It should be the other way around. But anyway, we're going to have work done by our electric field equaling the kinetic energy of our chlorine ion. So we get this. Now notice that we can't actually work out the speed here, because we don't know the mass, right? The mass is actually what we're trying to find. Nevertheless, at least we have an expression for V. So then we're going to go over to our circular motion. So in other words, Newton's second law, where in this case, the only unbalanced force is the magnetic force. And that equals mv squared over r, right? That's the circular motion. Newton's second law for circular motion. So then again, we have QVB equals mv squared over r. We can do a little bit of cancellation of the v, and we get this expression. So now we have two expressions. One expression for v that came from our energy conservation, and one expression for v that came from our thinking about the magnetic forces. And really, we don't care what that v is, but we know that they has to be the same, because whatever the v, whatever speed it came out of the accelerator with is going to be the same speed that it enters the magnetic field with. So we can set those two equal. And then we're going to isolate for our mass, right? That's the basic idea. So this is a bit of a mess here, but if we square both sides, then you can see a couple of cancellations will occur. We can divide charge. One of the charges, we can divide charge from both sides, and we can divide mass from both sides. And so we get this nice expression. Well, it's not that nice, but you know what I mean. We get a nice closed form expression for the mass, which is equal to charge times radius squared times magnetic field squared divided by 2 times the potential difference. And we have all those numbers, and if we plug them in, we get that the mass of the chlorine plus ion is 5.83 times 10 to the negative 6 kilograms. Okay? So that's the basic idea there. Again, that's typically how these kinds of questions are going to go. You're going to use some kind of energy conservation that will get you either get you your speed as a number or get you an expression for your speed, as was in the case here. And then you're going to use that in your magnetic force equation. So look out for this kind of strategy as you go forward. Here's some stuff to read over from the textbook. It basically just goes over much the same things I did, but in a lot more depth, and some questions to try on your own. Thanks for watching, folks. I'll see you next time.